Ladies and gentlemen, my name is Matt Brownlow, and today I'm going to be presenting to you flow around an object with the shallow water equations and penalization. So, if you click to the next slide, as you can see, this is our governing equations right here. So, with the shallow water equations in the light that are derived from Navier strokes of equations, the shallow water equations assume that the x and y velocities assume an assumption that z is the answer. Water equations assume that the x and y velocities are much greater than the z velocities.
This results in a
2D analysis instead of a 3D analysis. And as you can see, big H is the average height of the water, while little h is the deviation of the water. In the momentum equation, the spatial derivative of h is modeled from the hydrostatic pressure, which all in all means that this only depends on the height of the water. So the B term, which is the drag coefficient, and the F earth curvature terms are going to be ignored in this equation. So now that we have our general governing equation, we're going to add in an object for the flow to go around. But to do this, we have to add in penalization. So to do this, we're going to add in a mask in this top right corner. So all in all, the mass ever is going to be 0 everywhere outside of the object and 1 everywhere inside the object. You can use mathematical equations to define a shape like a circle, like I have done.
It's better to use
with a Gaussian or a Tinci, it's better to use a distribution system with using a Gaussian or a chance.
It's not Joe yet? Sorry, we're doing a presentation.
So it's better to use a Gaussian distribution or a Couch function, especially in the circle. And this is because if you just use the equation of a circle, it'll be choppy and numerically unstable. Use a function that uses the gravitational pull. So you have to use a function that will gradually pull the value up to 1, as you can see in this depiction here. See, I'm giving you little pauses. So now that we have our mass, we can add in a term to the equation, specifically the momentum equation. The term is 1 over lambda times the mass times the velocity. If you have a very small lambda, due to the rest of it being significantly smaller than the mass term, the solution of this equation is an exponential function. We want this for a controllable gradient so we can control our stability. I'm going to apply this to the momentum equation, but you also can apply this h to the penalization equation. Frick. Dang that. Shoot. Gosh darn it. I'm going to apply this to the momentum equation. We can also apply penalization to the h equation. These equations were discretized using central differentiation in space, including Euler's time discretization first order. This gives us second order accuracy in space and first order accuracy in time. The time set criteria was based off of Euler's 2D stability. So for the boundary conditions, the u velocity was 0 set at the left and right boundaries. And the derivative boundary condition was set at the top and the bottom. And the exact opposite was set for the v velocity. The derivative boundary conditions were set all around for h. So the solution for this, all in all, was built with a 3x3 domain that had a 0.3 grid spacing. In the x and y, h was initialized using a linear bump, and the velocities were initialized at 0. Time runs until t is greater than 2, and it plots every 2,500 iterations. So you can see all the moving parts in pieces with the solution here. All of the movements and parts are moving to where we like them to be moving to. This alone is the end result of the solution. This is the best visual representation of what's going on right now. So as you see the wave disperse and go around the circle. This is just a blown up version of the vector ball, so you can see the whole thing better. So, ladies and gentlemen, we appreciate you giving us our time. Thank you again. So, just for a wrap up, this was the presentation on flow around an object with the shallow water equations of penalization. I hope you enjoyed our time. Thank you.